Dear students, here in this video we are going to explain atomic spectra. As we know that each element has a characteristic line spectrum. As the atomic stability and existence of lines, spectral lines or discrete lines are the important aspects of the atom that find the no explanation in classical mechanics. So here we are going to explain the atomic spectra. As atomic spectra, to explain it, we will take our start with the quantization of energy. Quantization of energy. So quantization of energy is related to the discovery of photon. Discovery of photon, and which says that the light consists of discrete packet of energies. Discrete packets of energy. So these are this is the indivisible amount of energy which we cannot further divide it. So light consists of discrete packets of energy which are called as photons. So there are the different models which explain the atomic structure, and so combining the Rutherford atomic model, there was a Rutherford model, planetary models, which was based on the motion of the planets around the sun. So it is also called as Rutherford planetary model. And then there was other the and also combining the Planck quantum hypothesis, Planck quantum hypothesis, and then there was another phenomena, that was the photon, Einstein concept of the photon, Einstein concept of photon, and then there was the Bohr atomic model. So we can combine all these phenomena, all these important discoveries, and then we comes to the present Bohr atomic model. As you know that in the Rutherford atomic model, Rutherford gives the atomic model in which the electron uh, circulate around the nucleus, but he cannot explain the stability of atom. So its drawback was that he cannot explain the stability of the atom, as we know that the moving charged particle continuously emitting the electromagnetic radiations by losing its energy, and though so if there is the nucleus, so electron continuously revolving around the nucleus, continuously emitting the electromagnetic radiation, and they falls into the nucleus. So there was so the Rutherford atomic model cannot explain the stability of atoms. So then there was another Planck quantum hypothesis, as the Planck was the first one who said that the energy is transferred in discrete amount which is equals to the h mu, and this discrete amount of energy is called as quanta. So he gives us the concept of light quanta, and so he was explaining the black body radiation, and he said that the energy transferred between the wall of the cavity and radiation in the form of discrete or indivisible amount of energy which is called as quanta, and its energy is equals to h mu. And then later on there was Einstein said that Einstein chose the Planck hypothesis, and he said that the radiation itself consists of discrete packets of energy. This radiation not only transfers its amount of energy in discrete form, rather the radiation itself consists of discrete packet of energy is equals to h mu, which are called as photon, which was later on given the name photon. So then there was the Bohr atomic model. Bohr proposed his atomic model in 1913. In 1913, he proposed atomic model and then that accurately account for the atomic spectrum of hydrogen atom. He in this model he used the concept of quantization of energy. So he accurately used the quantization of energy to explain the spectrum of hydrogen atom. What Bohr said, according to the Bohr atomic model, the atom consists of a tensor pod, which is called as the nucleus, which has the proton and neutron, and then there are the electron which moves in the circular orbit around the nucleus. So according to the Bohr concept gives the concept of quantization of energy. So important aspect again was the quantization of energy levels. Quantization of energy levels said that according to this concept that there are allowed energy level. There are allowed energy levels, and these allowed energy levels which has the total angular momentum L, for which total angular momentum L is equals to integral multiple of h cut, where h this is called as the also called as the Bohr quantization rule. This is also called as Bohr quantization rule. So the Bohr accurately used the quantization of energy in the and he extended to the quantization of energy level, and he said that within the atom there are allowed energy states for which the total angular momentum is equal to integral multiple of h cut. So these are the circular stable orbit. These are circular stable orbit, which are also called as stationary states. We also call them the stationary states and also called as discrete energy levels. These are also called as discrete energy levels, as uh, we can represent them with energy E1, E2, E3 up to so on. So each energy level within the hydrogen atom have only a discrete amount of energy and only discrete amount of energy. So as long as the electron move in a specific energy orbit, these are well localized energy levels. Stationary are also called as stationary state. Electron neither emit nor absorb energy. So these energy levels are called as allowed energy level. And so energy of this level, we can find the energy by formula E n is equals to minus r over n square, and here r is the Rydberg constant and r is the constant, and value of r is equals to e divided by 2 h square into e square over 4 pi epsilon naught r whole square. And so its value is almost equals to 13.6 electron volt. So we can write the En as minus 13.6 divided by n square. Here n represents the energy level, n is equals to 1, 2, 3 up to so on. So it represents the energy level, and here the minus sign comes due to the bound state nature of an atom. So it is due to the bound state nature of atom, as the atom is bind to the nucleus under some nuclear forces. Nucleus is exerting the forces, destructive forces on the electron, so the electron is bind within that state. So this is the bound state of nature of the electron. So this negative sign is due to this nature of electron, nature of atom. So here we can calculate the different spectral series for the hydrogen atom. And so here n represents the different states. So for n is equals to 1, and then we can have n is equals to 2, n is equal to 3, 4, and then n can be equals to 5, 6, and then we comes to different continuum states up to so on, n is equals to infinity. So the emission and absorption of the photon is accompanied by the jump in the energy of atom from one permitted value to another permitted value. That is, we say that as long as the electron move in a specific energy level, they neither absorb nor emit the energy. They will emit or absorb the energy in the form of photon, whose energy is equal to h mu when there is the jump in electron from one permitted energy state EI to another energy state EJ. So this much amount of energy will be accompanied by whenever there is a jump from one energy state to another energy state. These can be the emission, or this can be the absorption of photon. So let's first talk about when the electrons, spectral series of hydrogen atom. Spectral series of hydrogen atom corresponds to whenever electron jump from higher orbit from n is equals to 2 to n is equals to 1, n is equals to 3, either it will be equals to n is equals to 4, n is equals to 5, or either it can be the n is equals to 6. Whenever they jump from higher energy levels to the lower energy level, that is n is equals to 1, then this series is called as the Lyman series. So this series will be called as Lyman series of hydrogen atom. So this last line is called as the series limit. And in the same way, the second series, which is also called as the Balmer series, which correspond to the emission jump from higher orbit to the lower n is equals to 2 shell. So whenever there is the transition from higher energy level to n is equals to 2, so these are called as Balmer series. And so in the same way we can get the other series like Bastion series when there is the jump in the different electron from higher energy levels to n is equals to 3. So this will be the Bastion series, and in the same way we can get the Bragg and Fond series. So here the energy we know that is equals to EI minus EJ. j will be equals to E1 into 1 over n square I minus 1 over n square j, as we know that En is equals to E1 over n square, as we have already discussed, as it's equals to 13.6 electron volt divided by n square, and 13.6 electron volt is the energy of first Bohr orbit. And so correspondingly their frequency will be equals to, it will be equals to E I minus E F over H, as the frequency is equals to delta E divided by H. And so here again we can write it like, it will be equals to minus E1 over H into 1 over n square F minus 1 over n square I. And so this will be equals to frequency, and correspondingly we can also write the wavelength, as the wavelength we know that lambda is equal to c over mu, and so 1 over lambda will be equals to mu divided by c. So 1 over lambda will be equals to E1 over CH into 1 over n square F minus 1 over n square I. So here we can write it as always n square, ni is always greater than nf. So for the Lemon series we can write the formula as nf will be equals to 1, and its formula will be equals to E1 over CH into 1 over 1 square minus 1 over n square F. So here the ni square, so here n can be equals to 2, 3, 4, it can be any higher energy. And so for the Balmer series we can write the formula nf is equals to 2, so it is equals to E1 over CH into, it will be equals to 1 over 2 square minus 1 over n square. So here n start with the 3, 4, 5 up to so on. And similarly for the Paston series, Paston nf will be equals to 3. So for this one, 1 over lambda will be equals to E1 over CH into 1 over 3 square minus 1 over n square. Again n will be equals to 4, 5, 6, and then bracket series for which the nf is equals to 4. So 1 over lambda will be equals to E1 over CH into 1 over 4 square minus 1 over n square. So here n star will be equals to 5, 6 up to so on, and then we comes to Ferns series for which nf is equals to 5, and for which 1 over lambda is equals to E1 divided by CH into 1 over 5 square minus 1 over n square. So here the ni will start from 6, 7 up to so on. So for each case here you can see that for every case ni is greater than nf. So as the final state is here, the initial state is and for the Lemon series first line is due to from whenever there is the jump in energy from n is equals to 2 to n is equals to 1, and second line will correspond to n is equal to 3 to n is equal to 1. And similarly for the Balmer series, the first spectral line will be due to and jump in electron from n is equal to 3 to n is equal to 2. Second will be n is equal to 4 to n is equal to 2, and so on. So here in this way we can get the different spectral lines within the hydrogen atom. So from the frequency and wavelength we can recognize from these value that the region of these lines in the electromagnetic spectrum, as the lemon which is corresponds to the ultraviolet region, Balmer series lies in the visible region of electromagnetic spectrum, and Paschen and red and front, these are in the infrared region of electromagnetic spectrum. So now we explain the type of spectrum, and we have two types of the line spectrum. Number one, emission line spectrum, emission line spectrum, and then we have the absorption line spectrum, absorption line spectrum. So here we get the two type of spectrum. So first, as we know that we have um, the matter condense type the matter in the condensed phase, that is in the solid and liquid phase, and there is the gaseous phase. Okay, so usually matter exists in these three phases, and so in the case of solid and liquid, as we know that the condensed matter at all temperature emits the radiation. So like the liquid and gases, we say that these emits the emit radiation at all temperature. So which have the wavelength present, all the wavelength are present in these radiations, so though with the different intensities. So the observed feature of these radiation were explained by the Planck, and so uh, he tells us that, as the Planck tells us that liquid and solid phases emits the radiation at all temperature, but without reference to their origin, that how they are emitted, how they are emitted, and what is their nature. So at that time, we in this case we have the collective behavior of the radiation. Collective behavior, radiation emitted were collective behavior of all interacting atom, not of a characteristic single atom. It's a collective behavior of all interacting atom. So it was not the characteristic behavior of, it was not about the characteristic behavior of a particular atoms or molecule, of particular atom or molecule. Rather, it was the collective behavior of all atoms or interacting atoms or molecules. So on the other extreme we have the gases. So in rarefied gases, atoms and molecules are so far apart. On the average, they interact only during the occasional collision. So Under these circumstances, we would accept the radiation emitted by the gases. So these emitted radiation to be the characteristic of particular atom or molecule. So these will be the characteristic of particular atom or molecule rather than the collective behavior of all interacting atom as in the case of solid and gases. So when atom or molecules in the vapor phase, in the vapor or gas phase, when they are excited at somewhat at less than the atmospheric pressure is, then they are suitably excited by passing an electric current, by passing an electric current through them. Then what happens when these atoms get excited? As we have E1 ground state and there is an other higher energy state, so electron jump from lower to higher energy state. So as a result, when it de-excite to lower energy state, then it will emit the radiation in the form of photon h mu. So then when we observe the spectrum, then this spectrum will be is called as emission line spectrum. So this is called as emission line spectrum, in which the electron jump from higher energy state to the lower energy state by emitting the photon of energy h mu. And similarly, when a white light is passed, for example, this is the rarefied gas, when we pass a white light to this rarefied gas, and then the resulting radiation which are transmitted through it. So here this rarefied gas will absorb some frequency or wavelength. So some wavelength or frequency will be absorbed by this wavelength, and resulting will be the absorption line spectrum. So again we will get the discrete line, but these will be the absorption line spectrum. So in this case, when we pass a light through it, so by absorbing the light, electron goes to the higher energy state, and so this absorption, correspondingly we have the absorption line spectrum. So emission line spectrum, which is emission line spectrum which has the bright fringes, bright line with the dark background. And in the case of absorption line spectrum, we have the dark lines with the bright background. So we can differentiate the absorption line spectrum from the emission bright spectrum from their appearance, as the emission line spectrum consists of bright line with dark background, and absorption line spectrum consists of with the dot line with bright background. So dot line corresponds to the absorbed frequency or wavelength by the gas. So in the spectrum of the sun which is the consist of white lights, in the spectrum of sun we can see the dot lines. So the dot line in the spectrum of sun are due to the fact, as we know that as the sun is the hot body, we know that although it emits a radiation, so its spectrum should be the emission line spectrum, but rather we have some dark line as well which corresponds to the absorption line spectrum. These lines are due to the fact that there are some gases around the sun, and so when the radiations emitted by the sun can and these gases absorb some of the radiations which are emitted by the sun, so as a result we can have some dark line in the spectrum of the sun which correspond to the absorbed wavelength or frequency by these gaseous core around the sun. Now we comes to the origin of line spectrum. So what is origin of discrete line spectrum? According to the Bohr atomic model, when electrons jump from higher energy state to the lower energy state, suppose these are the two energy levels E1 and 2. Electron jump from the higher energy levels to the lower energy levels, and this jump in energy accompanied by the emission of the photon of energy h mu. So emitted energy is as a single photon of light. So according to this model, the electron can exist only in atom in a certain specific energy level, rather in the E1 or E2 or E3 energy level they can uh, stay only in the certain specific energy level. So jump of an electron from one level to another level, so it's accompanied by the difference in the energy. Delta E should be is equals to h mu, should be equals to ei minus ef. So it should have this much amount of energy. So energy emitted energy should be equals to the difference in between the two energy levels. So it should gives off all energy at once in the form of single photon rather than in some gradual manner, because electron can never stay in between these two levels. It will always stay rather here at this point. It cannot stay here or at this point. It will either stay in the E2 state or E1 state. So these E1 and E2 are the allowed energy levels. These are allowed energy levels. So electron can never stay in between in these two states. So it can never emit the energy in some gradual manner. It will always emit the energy in the discrete packets of energy are all it at once to a single photon rather than in some gradual manner. So this difference, this emitted energy will be equals to the difference in the energy of these two levels in which there are the transitions. So delta E is equals to h mu E1 E I minus EF or E1 minus E2 here in this case. So this energy, as the energy is emitted always in the discrete form, so correspondingly we have the discrete line spectrum. So the origin of this discrete line spectrum lies in the discrete energy levels, allowed energy states, because electron can never stay between the energy level. It will only jump from one energy level to another energy level all at once, giving the energy to a single photon rather than in some gradual manner. So this is the origin of discrete line spectrum. So here we can best understand it with the help of an example. So what is the longest wavelength of Balmer series of hydrogen atom? What is the longest wavelength in the Balmer series of hydrogen atom? So the longest wavelength in the Balmer series of hydrogen atom can be find out at the longest wavelength is whenever NF is equals to, for the Balmer series we know that NF is equals to 2. So when Ni is equals to 3. So the longest wavelength corresponds to 1 over lambda is equals to R into 1 over n square F minus 1 over n square I, and so it will be equals to R into 1 over 2 square minus 1 over 3 square, and it will be equals to 0.139 R, and so correspondingly R lambda will be equals to 656 nanometer. So 656 nanometer wavelength is near the red end of visible spectrum. This is the red end of visible spectrum. As for example, if we have the three energy level, E3, this one is E2, and this one is E1. So there is the energy difference is delta E, and this difference is delta E is equals to E3 minus E1, and this one is E2 minus E1. So small energy difference, as energy difference between E2 and E1 is less than the energy difference between E3 and E1. So small energy difference correspond to the small frequency and longer wavelength, and large energy difference correspond to the large frequency and correspondingly small wavelength. As the wavelength and the frequency has inverse relation, so and the red line which correspond to n is equals to n1 energy level, and so it has the longer wavelength and small frequency. On the other extreme, when there is the jump from E6 to n is equals to uh, 2, final state is n is equal to 2, from n6 energy level we get the ultraviolet and or ultraviolet line, because there the energy difference is large between the two energy level corresponding to large frequency and smaller wavelength. So it depends on the difference between two energy levels. Now we will explain that how the existence of discrete energy level was independently confirmed by Frank Hertz's experiment. So now we comes to the Frank Hertz experiment. So according to the Bohr model of energy level, energy emitted and absorbed during when electron jump from high energy level to lower energy level. So again I will make the energy state E1 and E2 Bohr energy levels. These are the two, for example, two Bohr energy level. When electron jump from higher to the lower or from lower to higher orbit, so there will be the absorption of electron when it jump from lower to higher. Photon of energy h mu is absorbed, and when it jump from higher to lower, a photon of energy h mu is emitted. So the jump in these emission of energy correspond to the emission line spectrum and emission absorb absorption line spectrum. So the discrete line spectrum, as we already discussed, that it can be the emission and absorption line spectrum. So the Frank Hertz was the first one who experimentally confirmed the presence of discrete energy levels by his experiment. So now, uh, what is the setup of? Was the setup of uh, Frank Hertz experiment? He The experiment was to demonstrate that discrete energy level exist, and furthermore that they are the same as suggested by the line spectrum. So this was a glass tube containing the different element in the vapor phase, and so there were the two plates. So this was the filament, and so here this was the collecting plate. This plate is called as collecting plate. So this was the source of electron. Maybe this can be the thermal electron, can be emitted by thermionic emission. So the source of electron, and here was the micro emitter to read the current, and so this was connected to the battery. Here they develop the potential difference. This is the grid. So here he developed the small potential difference between grid and collecting plate. So this was the grid. So this setup was like this one. So this was the whole setup. So Frank and Hertz bombarded the vapor of various elements with the electron of known kinetic energy. So this was the source of electron. Electron was created by thermionic emission. So electron was of the known energy. So there was this different element within the glass tube which were in the vapor phase. So the various vapor of various elements were bombarded with the electron of known kinetic energy. So here he developed the potential difference between grid and this collecting plate. And so this potential difference was developed between the collecting plate and grid that prevent the electron having the energy less than certain minimum energy from contributing to the current, and it prevents the electron to reach the collecting plate and to contribute to the to contribute the electron to the current, which can be shown by ammeter. So the electron having the less energy, less than certain minimum energy, cannot reach the collecting plate. So this potential prevent them from contributing to the current I in the ammeter. So as the accelerating voltage is increased, when he increased the accelerating voltage, and more electron will arrive at the plate. As a result, the current rises. It will rise the current if the kinetic energy is conserved. If kinetic energy is conserved, then what happen? If kinetic energy of electron is conserved, then electron collide with one of the atom in the vapor. Electron with the vapor, the electron nearly bounces off. So vapor is the larger in size, electron is smaller in size. So when it hit the electron, collide the vapor, it will be bounces back. As the ion, as the atom, vapor atom is much heavier than the electron, so it will lose no energy in this process. After certain critical energy is reached, however, the plate current drops down to zero after reaching the some critical energy. So this drop of current shows that it suggests that the electron colliding with the atom, with one of the atom, and give off its all of its energy to excite the atom to an energy level above its ground state. So such a collision are called as inelastic collision. As we know that collisions are of the two type. It can be the elastic or it can be the inelastic. So in contrast to the elastic collision are the one in which the kinetic energy is conserved. So the critical energy of electron is equals to the energy which needed to raise the atom to its lowest excited state. So for example, this one is the ground state and this one is the lowest excited state. So whenever we increase the accelerating voltage and the kinetic energy of electron reaches to its some critical value, so this critical amount of energy is that energy of the electron which is equal to the energy which needed to raise this electron from ground state to some excited state. So as the accelerating voltage is further, the blunt this plate current again drops down to drops down. Okay, when we increase the accelerating voltage is raised, the plate current again increases, since now the electron having the enough energy to reach the plate, and the plate of as a result, so the plate current rises as the more electron reach the collecting plate as we increase the accelerating voltage. But after some time there is again a sharp drop down in the plate current, which is due to another elastic collision of electron with another atom, and to raise it to the its lowest excited energy state. So due to this transfer of energy and due to this excitation of atom, there is the again drop down in the plate current. So again we repeat the process. When again we increase the accelerating voltage, when we increase the accelerating voltage, as a result the plate more and more electron arrive at the collecting plate. As a result, the ammeter shows the rise in current. So again, when critical energy is reached, the electron will transfer all of its energy to another atom in the to rise it to the same excited state, and again there will be the drop down in the current shown by the ammeter. So in this way, so the series of critical potential is obtained for the atomic vapor is obtained. So its plot will be like this one. So this one is your y-axis and this one is x-axis. So on x-axis he shows the accelerating voltage was on x-axis, and then on y-axis he shows the plate current. Plate current is the accelerating voltage 0, 2, 4, 6, 8, 10, 12 up to 1, and then as we increase the accelerating voltage, the plate current increases. After some critical value is reached, it drops down to lower energy level. Then again we increase the plate current, we get another peak, and then it again drops down to 0, and then in this way we get a different peaks. So we get a critical potential, series of critical potential is obtained. So whenever plate current reaches, for each value it reaches is some critical value, and then there will be a sharp drop down after some critical value. So this sharp uh, is drop down in the plate current is due to inelastic collision. Inelastic collision of atom of electron with atom with vapor atom, and so it goes to the excited state. So again it, when we increase the accelerating voltage, the electron reach to its critical value, and again it has the enough energy to excite another atom, and so when it excites another atom, as a result it again plate current drops down to 0. So in this way get a series of this peak. So to check the critical potentials that were due to the atomic levels, the Frank and Hurt observed the emission spectra of the vapors during the electron bombardment. So when electron bombarded the atom, it goes to the excited state, and when atom get de-excite by the emission of radiation, by the emitting the photon of energy h mu. So when Frank and Hertz observed this emission spectra of the vapor during the electron bombardment, it was confirmed that it was the emission, that it was the discrete line spectrum as it was interpreted by the Bohr. So he was the first one who by explained the or observed the discrete line spectrum by an independent experiment. So this was the first experiment of uh, discrete energy level. Thanks for watching. For more videos, please subscribe our channel.